There we go. All right, I think we're recording. Are we hot? All right, we're hot. All right, we're halfway there, guys. Isn't that crazy? It's already halfway. We're halfway through this thing. Nuts, nuts. Crazy how fast time is going by. I hope you guys are doing well and staying on top of your work. Speaking of work, what the heck happened on homework 3? Why was everyone so like quiet about homework? Like, what happened? Was there like something that went wrong? Like, I don't think anyone submitted homework 3. I don't know. I'm looking on the grades on the Canvas, but it looks like most of you guys didn't hand in homework 3. So like, what? Any any words? Any thoughts? Anything? Was that the one that you guys were just like, no, I don't. I'm not gonna do this one, or like, what was it?
Some of the questions were a bit iffy. I should have asked about it, so like that made me push it later. So when it was time to submit, it was too late and it closed off.
Okay, appreciate the honesty, but I mean that's no excuse. I didn't understand the question. Okay, fine, then we'll ask it during tutoring, or ask us for help. What I've kind of been telling you guys to do for the past couple classes. So, all right, I mean, if you guys are fine with your grade taking a toll, then all right. I mean, the midterm, honestly, it is a huge chunk of your grade, but these homeworks are supposed to be like saving graces. These quizzes are supposed to be like, the saving graces. The attendance quizzes are supposed to be like the grade boosters. So, if you're slacking on those stuff and only shooting for the midterm and final, you're gambling. You're dancing with the devil, and you're it's not a good idea to do that. If it's an issue about like, I'm not really sure how to prioritize my work, or I'm having a hard time with that, well then you gotta let your counselors know. You gotta let us know. You gotta make sure like you gotta make sure you're doing something about it. But whatever. I've said my spiel last class about it. If you don't remember, go to the YouTube video. I pretty much yelled at you guys for the first 15 minutes. So, I mean, I'm not really going to repeat myself at this point. Also, because my throat is killing me. Homework number 4 is due tomorrow. Yes, your homework is due tomorrow. And the reason why the reason why we're making a homework for due tomorrow is because homework 4 material is on the midterm. So it makes sense. I believe lecture 5 material is also on the midterm. It's the polar coordinate stuff that we just learned. So is it up? Is it up yet? Homework 5? Or has there been homework that's assigned that has polar coordinates on there?
I don't think so, but I could be wrong.
Don't think so.
I don't think so either. No.
Okay, all right. Well, then you guys should probably ask a lot of polar coordinate questions during recitation tomorrow then, and make sure you guys are solid on that for the midterm. That's on Wednesday, because your midterm is on Wednesday. Some quick reminders about the midterm. It's going to cover everything from lecture 1 to lecture 5, everything from volumes of revolution and the area under the curve, all the way up to polar coordinates, and the stuff we did last class on polar coordinates, right? That was it. That's all we did for last class, right? I put up the supplemental video from last year. It just kind of worked out where like the stuff I couldn't get to last year actually was the stuff I couldn't get to this year. So it was pretty whatchamacallit, fortunate that I didn't have to make another video. And then what else? Oh, so yeah, so you're gonna notice the homework 5, the one that gets assigned tomorrow. Okay, if you guys aren't listening, please listen. There's going to be a homework that's assigned tomorrow at the end of recitation. However, that homework will not be due on Thursday. The reason for this is we want you guys to focus on studying for the midterm. You understand? Thanks, John.
Thank you. We
Welcome.
appreciate it so much.
Yeah. Thank you. All right. At least someone said it. All right.
I had to.
Yeah, I want you guys to please focus on. I'm gonna leave and rejoin. Audio's cut. Okay, what is going on? It rained last night, didn't it? It didn't. It's not like it. Are you guys having like connectivity issues? No.
I don't know.
Yeah,
I
my
might
Wi-Fi
have
comes in
connectivity
and out.
issues too because it's about to start raining where I am.
Oh, okay. All right. Well, if you get disconnected, just check out the video, I guess. That's what I do for this specific reason. So yeah, if you get DC'd, just check out the video later on. All right. What was I saying? Homework 5 is due Friday. I asked Gina what time, and she was like end of the day, and I'm like, I don't. All right. I mean, that can mean like a lot of different things. So I'm gonna assume that she means like post class. So I think she's being nice to you guys. You guys should really appreciate her. She does a lot for you guys, believe it or not. So she's gonna give you extra time on the homework 5 as well. All right. Any questions so far on what's coming up? Are you guys staying on top of your due dates? I'm just letting you guys know in college they don't do what I'm doing right now. I do this, I do all of this, right, for you. Like I let you guys know like the upcoming due dates and stuff like that. You should be doing that. You should be doing that for like all your classes, right? And making sure that you're staying on top of your due dates and stuff. All right. So I don't think it's like babying you guys.
Appreciate it.
I don't think it's a babying you guys, but I think of it as building good habits, and I really want you guys to do this at the start of like every single lecture. You know, like lecture, whatever number, whatever, and then write down the important dates, just so that when you go back to your notes, you're like, oh yeah, I got to do the X, Y, and Z and stuff like that. Okay. Okay. Any questions from lecture 5 with the polar coordinates and stuff like that? Once again, I'm not going to make you guys like memorize like the butt graph or like what does a circle look like, or what does a 7-petal thing look like, or anything like that. That's gonna be that's way too much to put on you guys, but they will expect you guys to be able to do that when you do take this class. I'm just letting you guys know. All right. So what else? If you watch the supplemental video, it shows you how to find area between two polar curves. I think we started one last class. I think I'm gonna ask Gina to finish that one in recitation, along with any other polar stuff that I may have forgotten. But that's it. Like we've covered everything that's gonna be on this midterm on Wednesday. Okay. You guys should not wait until Wednesday morning to start studying. Oh, that means we could start just Tuesday night, right? No, like you guys should be already studying. Like you guys should have studied over the weekend. You guys should be studying now. Like as soon as this class is over. Or do you have another class after this? You have something after this, I think, right? Just tutoring?
Tutoring after this.
Oh, perfect. So there you go. Oh, is that why you guys are always just like out of it and tired and just unresponsive? Because I got you at the end.
It's partially the reason why. I'm not gonna lie.
Yeah, I mean, like
I'm gonna be
depends.
honest.
Sometimes, like,
Whatever. I just gave you guys another excuse. That's what I don't want to do. All right, whatever. All right. Anyways, so please start studying now. Don't wait till later. All right. If there's no questions on lecture 5, I can just jump right into chapter 10. You guys okay with that?
Yes, sir.
You guys ready? You guys ready to dive in?
No, not really, but hey, man, the show must go on.
It absolutely does. Winter is finally here, ladies and gentlemen. We're talking about sequences and series for the rest of this program. All right. It's going to get crazy. And I'm going to warn you guys, and I think I said this last class too, it gets harder and harder and harder and crazier from here. So if you're like drowning now, you got to doggy paddle out of it. You got to get yourself out and then get on top again. All right. Because it's going to get crazier from here. I'm just letting you guys know. You think I was meticulous before? You haven't seen nothing yet. All right. With some of these sequences and series stuff, you have to be super duper specific in your responses. I'm going to be telling you guys what I'm looking for, what they're looking for, right? And if you miss those things, I have to dock you for it, unfortunately. So that means like things like writing an answer with no work, that's not going to fly at all. All right. It's immediate 0 if you do that, right? It's about the how. It's more about the how than the what at the end, like at the end of your work. All right. Okay, here we go. Sequences. We're talking about sequences. We are on PDF page 553. We're in chapter 10 now, right? If you guys remember, chapter 9 was the stuff we did with logistic growth and differential equations. Chapter 11 was polar functions and parametric functions. We skipped chapter 10 because chapter 10 is its own crazy thing. So we're starting with 10.1, starts with sequences. Sequences is not something that most of you have probably seen sequences before, or like understand inherently like what a sequence is. But to start off, let's start off with some definitions. Yeah, like what is a sequence? How do we define a sequence? How do we notate How do you do notation with a sequence and stuff like that? All right. So let's start with a definition. All right, what is a sequence? I would say it's like this is like what is it? The abridged, Cliff Notes version of like what the true definition of a sequence is, but it's basically a string of numbers. I'm sorry, I should say a pattern of numbers. There we go. A pattern of numbers separated by commas. That are defined by a specific rule. Pattern numbers, usually it's separated by a comma, and this pattern is generated with some sort of rule. And this rule, the word rule, it's super duper flexible. All right, the rule is going to determine your domain, the numbers that you can put into your sequence, as, or in other words, your index. It's another fancy word for it. And it's going to determine the output, how your numbers are generated, if that makes sense, right? For notation, they usually, I don't know, some people are different, but they usually do some sort of a sub n, some letter sub n, and the n is called the index. It's like right? You guys know what an index is of a book. You guys know what books are, right? Those things that are made out of paper. You open them up, and the first page or so, you got a table of contents, right? Index, it tells you what like term you're on, essentially. Okay. And they use, it could be A, it could be B, it could be C, whatever letter to define the sequence. Sometimes they do this. That tells you like the starting sequence, I'm sorry, the starting index value, right? That means it starts at 1. It could start at 2, it could start at 5, it could start at 0, it could start at whatever you want it to. But usually it starts at 0 or 1, right? And it's generated like a sub 0, a sub 1, a sub 2, dot, 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 a sub n, dot, 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 all the way out to infinity if we wanted to. Questions so far on the notation and stuff like that? Now sequences are different from functions in their own ways, but they are similar also. The limit rules for functions, do you guys know what the limit rules are for functions? Like if I take the limit of 2 functions being added to each other, you can like split it up into 2 limits. Have you guys ever seen that before?
Yeah.
Maybe, kind of.
Yeah, I think I know what you're talking about, but maybe.
Ready? The limit of the sum is the sum of the limits. This is just one of the examples. This is one example of one of the limit rules. So basically, if you have a limit on the opposite, on the outside of 2 functions being added or subtracted or multiplied to each other, right? You can actually just break up the 2 functions and then, right, compute the limit separately. These are basic limit rules that you guys should have learned. I'm just gonna dot this. Lim rules.
Yeah, I knew these. Like I know what you're talking about now.
All right, good. I think you guys learned this in pre-calc and stuff, but I'm saying things like that, things like the limit rules and stuff, they actually transfer over nicely with sequences. I would say the only difference, right? So like technically you can think of this as like a function of n, right? My input is my index values, but the catch is n is, how do I define this? N values, sorry. N values are, I guess you could go negative, but usually, I'm going to use this loosely here, usually positive integers, meaning your inputs cannot be decimals. Like you can't have any You can't plug in 2.2, right? These have to be sequential numbers because they refer to an order. Does that make sense? Any questions so far? You sure? This is the easy stuff. This is the basic stuff. All right, cool. If there's no questions, I'm gonna move on. Well, oh yeah. So the book has some examples of sequences. I think they're on page like 554. Right. So examples of sequences. For example, close example one. A sub n is equal to 1 minus 1 over n. And usually they have to denote some sort of like domain. They have to tell you your starting point. If they don't tell you a starting point, then you don't know what sequence is being generated specifically, right? You could either be leaving out a term, you could be leaving out 2 terms, you could be leaving out a bunch of terms. But if they don't tell you where to start, then you don't know where the sequence starts, you know what I mean? So they need to tell you, they use the word domain, you use starting point, whatever words float your boat, whatever makes sense to you, all right? So what does the sequence look like? Well, oh, whoops. So it's gonna, essentially all you do, you're just plugging in numbers, right? So you plug in 1 first. What do we get? That's 1 minus 1 over 1, 0. That's my first term. That's a sub 1. Make sense? A sub 2 is gonna be when I plug 2 in, because I'm starting at 1. So 1 minus 1/2, what is that? That's 1/2. Is that okay? Do I need to keep going? I'll do one more. All right, ready? A sub 3. That's my third term because I'm starting at 1. So 1 minus 1/3 is, looks like 2/3. Is this right? Now, okay, so what this said, why this chapter is hard. One reason, there's a bunch of reasons why it's hard, but why this chapter is hard, a reason is because some people are not good at pattern recognition, either because they just haven't been exposed to it a lot, or they just haven't played enough Zelda games to figure out, like, you know, like puzzles and things like that, right? So so some of you might pick up on this quickly, some of you may not, all right? But for what I want you guys to do is plug in as many values as you need to figure out the pattern. What do I mean by that? So after plugging in the third one here, right? I don't really need to plug in the fourth one and do the algebra anymore. There's a pattern that emerges, and I don't know if you guys see it. Do you guys see it? Maybe if I do this. Do you guys see a pattern that emerges?
Yeah.
You want to?
I mean, like, I think,
yeah.
Yeah, I think of it like in a weird way, but I was thinking like it's like 0, 1/2, so it's like 0, 1, 2. Then the next one is like 2, 3. Next one is gonna be 3, 4. Next one's gonna be 4, 5. You know, like
no, that's not weird, Waldo. Why are you saying that's weird? Why are you shaming like the people that think that way, man? Because there are probably a bunch of people that think the same way. I think the same way too, right? I see 0 over 1, and then the next one is 1 over 2, then 2 over 3, then 3 over 4, then 4 over 5, then 5 over 6, and so on and so forth, right? There's no algebra needed for that. It's you're recognizing the pattern. Do you guys see the difference, right? We had to do algebra to generate the first couple ones, but once we pick up on the pattern, yeah, it's gonna be 3 over 4, and 4 over 5, and so on and so forth. Yeah, do you guys see that? Does that make sense? Can I move on now? Yeah. Okay. This pattern recognition thing idea, it's something that's going to come up in with series 2. So just letting you guys know. All right. So if you want to see more examples of sequences, there's like a table. This is one of the examples in that table. I'm gonna just move on though. 2 types of sequences that exist. Well, not just 2, but the 2 that they kind of focus on. Ready? First one's called explicit. Next one's called recursive. And some of you guys might know recursion, or might have heard the word recursion before. Hopefully you guys are on that part with MATLAB, maybe. Did you guys do recursion in MATLAB yet? Or computer science, or anyone take a computer science class? No? Okay, it's all right, I'll explain it. So explicit, how do I define, how do I define an explicit sequence, right? Well, it just means that they give you, like this right here is an example of an explicit sequence. It's like they give you some formula, you plug in, and it just spits out the nth value. So it gives the nth term value. Kind of like a function, right? You plug in x, it'll spit out a y. You plug in an n, it'll give you the nth term. So if I plugged in 5, it would get me the 5th term. If I plug in 100, it would get me the 100th term, and so on and so forth. I guess depending on your domain, of course, but it gives you the nth term value. But there's another way to define a sequence. And that's what this is something that makes sequences and functions a little different, because you can't do this with functions. There's something called a recursively defined sequence, or you may have heard the word recursion. What is a recursive sequence? It's basically a sequence that calls itself within the sequence. It's like some Inception level stuff, you know. It's like the function. I'm sorry. There might be like a previous term that's defined within the function, and because of the way a recursive sequence is defined, you're always going to need a starting point along with the domain, right? Like the domain, that goes without saying, right? All sequences need a starting value, but what I mean is for recursively defined sequences, you need a starting like point, like a starting value. What am I talking about? So one common example of a recursive sequence is the Fibonacci sequence. Maybe some of you guys have heard this one before. Anyone? Fibonacci? Golden ratio? Phi?
I've heard of the Fibonacci ratio. Or the
Huh?
Fibonacci sequence.
What?
I've heard of the Fibonacci sequence.
Okay. Do you know anything about it?
I know that it has some kind of correlation with phi as you go late, like into the deep
Okay.
numbers.
So the definition of Fibonacci sequence. John, are you going to test us on the Fibonacci sequence? No, I'm showing you this because it's really, really interesting. It's one of the crazy things that exist in math, and also it deals with sequences. So I'm just putting it together. Okay, Fibonacci sequence is defined as they use f1 is equal to 1, f2 is equal to 1, and then the sequence is defined as f sub n minus 1 plus f sub n minus 2. What does that mean? It means that my first term is 1 and my second term is also 1. So if I were to string out the Fibonacci sequence, it goes 1, comma 1. And then it says after the second term, if I wanted to find f sub 3, well, let's do the calculations to figure that out, right? If I wanted to figure out f sub 3, well, that's the same thing as f sub 3 minus 1 plus f sub 3 minus 2, which simplifies down to f sub of 2 plus f sub 1. And maybe this will shed a little light of why we need a starting point. In this case, we have like 2 starting values, right? You could have 2, you could have 3, you could have 5, whatever. But the way this is defined, it's saying take the term before your nth term and the term before that and add them together. So in this case, we're going to take 1 and 1, add them together to generate 2. Does that make sense? Right? The next term is going to be 2 plus 1, which is 3. The next term is going to be 3 plus 2, which is 5. And then 8, and then 13, then 21, and then so on and so forth. Do you guys understand how this is being defined? And you guys see how there really isn't like a nice way. I'm sure there is an explicit definition for Fibonacci sequence, but it's much easier to compute it in this manner, if that makes sense, you know? So it's like, what this means is that sometimes explicit sequences are like easier to play with, you know? Sometimes recursive sequences are easier to play with. They both have their like ups and downs, their advantages and disadvantages. One of the an advantage of a recursive sequence is they're very easy to program. You guys are going to be engineers, hopefully. And you guys are gonna go into programming and stuff like that, you know, this is very easy to program. You tell the thing where you to start at, you tell what to do every single step after that, let it loop on itself forever and ever, and it can generate a certain term for you. So computing wise, recursive sequences are nice. We like that. Because we're gonna later on deal with like crazier looking explicit sequences. And those like are really hard to compute, or might be hard to compute, you know? So usually recursive sequences, they're very simple, if that makes sense. I don't know. I hope I did a good job explaining that. But some fun facts about the Fibonacci sequence. It starts to approach, if you take the ratio of a term with the term before it, and like as you go down later and later and later in the sequence, it starts to approach. And so what that means is if I take the limit as n goes to infinity of this Fibonacci sequence. Oh, wait, no, that's not true. Sorry. Limit as n goes to infinity of f n plus 1 over f sub n. So I'm saying if I take a term and then take the term before it and put them over each other, it starts to approach this 1.618 something 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 number. It's like this number that's found in math. It's called phi. It's called the golden ratio. There's a lot of like, it deals with spirals, and it deals with like sunflower petals, and like how like, you know, how like our galaxy like spins in a spiral. Anything with a spiral can like kind of go back to this. It's a very interesting phenomena that exists. People back in the day thought like if you had this ratio in your like face and stuff, they considered you beautiful, you know, no matter how non-beautiful you were. I was going to use the other word. All right, but anyways, but yeah, that's the more interesting stuff that doesn't really deal with what we're talking about here. So, but yes, recursive sequence, it basically calls itself over and over and over again. All right, explicit sequence, you can just plug in, it'll spit it out. Got it? Yeah.
Yes.
Yeah.
Okay. Can someone tell me what is an index of a sequence?
The n.
I'm not looking for one word answers. It doesn't have to be a one word answer. Someone said
It's
n.
a sub n.
It's what?
A sub n.
Okay. Anything
The
else?
starting point.
Yeah. Okay, fine. I like that. It's like your starting point for your sequence. Okay, sure.
It like indicates what term in the sequence you're looking at.
Yeah, right. So it doesn't necessarily have to be like, because it's defined as n, you know. So it could be like, it could be 100. You know, you could be looking at the 100th term, but you know, you got to watch out because like if you started at 0, then you'd be looking at the 99th term. You guys see what I'm saying? Like if I if I had a sequence that's defined as this, sorry, so on and so forth, right? This is the first term, even though it's sub 0, you know what I mean? So like a sub 99 would be the, I think I went backwards on that one, but a sub 99 would be the 100th term. Do you guys get what I'm saying? Like this is
Yeah, I
the,
get it.
Yeah, because
Third
it's like based
term-
on your starting point.
sorry, say that again, Waldo.
Oh no, because you're like it's based on your starting point, right? So like if you start at 0, 0 is still a value. So then like 99 would be like the 100th term.
Exactly. All right, so it's kind of easy to get lost a little bit with that. So that's why I'm saying like this is really important, your starting point. Okay. All right, let's move on. Let's bring some calc into this. I guess pre-calc. We're gonna take the limit of some sequences. And it's much easier to take the limit of an explicit sequence. So we're gonna really focus with those, but you can take the limit of a recursive sequence as well. It is a little trickier, but I mean, it's the same idea. You're just letting n go to infinity, essentially. Excuse me, sorry, the T. With the limit of a sequence, we want to see, does this thing converge? And there's that word again. Does it converge or diverge to a specific value? That's what we're checking for. All right. And this is not the right section. Why am I here? We're in 10.1. Right, so those limit rules that I was mentioning before, those are all gonna come into play, right? You can take the limit of multiple sequences, you can bring the limit in, you can bring the limit out. So let's just look at some examples here. Okay, ready? This is example, let's call this 2. So the example is asking, find the limit of this sequence. See if you've been paying attention. There we go. So it looks like this over that, comma, 3 squared minus 2 over 3 squared, 4 squared minus 2 over 4 squared. Dot, 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 dot. Let's say this is my, oh my gosh, that's a huge SN. All right, let's say this is my sequence. Here we go, ready? Let's see if you've been paying attention. Is this a explicitly defined sequence or an recursively defined sequence? What do you guys think?
Is it
Recursive?
explicit?
Explicit.
Explicit.
Recursive, since it replicates the Fibonacci sequence.
It doesn't replicate. Okay, hold on real quick. Fibonacci sequence was one like example of a recursive sequence. I'm not saying that all recursive sequences look like the Fibonacci sequence, so just watch out. Fibonacci sequence was a very, very specific example. But this one, okay, so I'm hearing a lot of people say explicit. Dan says recursive, but can I hear you guys like give me a reason, not just guess? Like, why do you guys think
Well,
it's explicit?
it would be explicit because it keeps going on and on with the n value. So it goes n equals to 2, n equals to 3, n equals to 4. So like it keeps going like with that same pattern. Like it's not adding them together like how you did before with the other one.
I know what
I
you're
feel
No,
like I'm on the
think-
right track. I just can't explain it right.
No, that's what I mean, guys. It's like you can't go to a professor and be like, you know what I'm trying to say? You know, like you can't say that to a professor. You need to be able to clearly, like, I kind of get what you're saying. I'm assuming that was Jeremy, right? But like I kind of get what you're saying, but like you should be able to clearly explain. What I heard, the way I interpreted your response, Jeremy, was there's a pattern, therefore it's an explicit sequence. So I'm like, wait a minute, recursive sequences have patterns too.
But it's not exactly how I meant it. Like it
Right, I
has a
know.
pattern. It's a specific pattern though. Like it's like a formula that you're just plugging in
How did
different
I-
values in. Like
You do that for recursive sequences too. But I'm saying, how did I define recursive sequence? Oh, Justin, something to add.
Oh yeah, I was gonna say it's explicit because the pattern doesn't like it doesn't depend on the previous value.
Okay, so Justin is disproving the fact that this is a recursive sequence. So he's saying there's no way this is a recursive sequence. Okay, so that means recursive, it can't be a recursive sequence. He's right. It's not calling itself. That's how I define recursive sequence, right? There's no, I didn't give you a starting point, and I was like, the following terms come from that starting point. You know what I mean? So you know it's not a recursive sequence, but is this an explicitly defined sequence?
You said
Yes.
before that
because-
explicit, yeah. Well, Justin, I'll let you explain.
Can I, so how did I
because-
define an explicit sequence?
Explicit sequence, isn't it like
Let's take that
you
about-
can write it as an equation that can be used to like predict the
Okay, so
Upwards.
now, see, all right, Justin, you're too clever, man. So yes, you can write this as like some expression, right, involving an n, but do we have that on here?
no, we don't.
No. So it was a trick question, guys. It was a trick question. I got all of y'all. All right. You don't know what the explicit definition is yet. You can so Jeremy was kind of hinting at it, right? He was like, oh, there's a 2 and then a 3 and then a 4. So Jeremy was kind of getting the pattern down. Okay, that's fine. And then Justin was saying, oh shoot, what was Justin saying? Oh, Justin said we can get an equation that represents the scenario, but do we have one is the question.
No, we don't have one.
No, not yet. So let's figure it out first. Let's figure out the explicit definition first, because I think it's pretty easy to see it. In fact, I mean, Jeremy, do you have it? You kind of said it. You were hinting at it before.
So it would be well, it'd be n plus 1 squared minus 2, and then n plus 1 squared at the bottom, right? Or
Oh,
no?
interesting. I see what you're saying. Okay, but there's one important.
If that's if n is starting at 1, that's if
There it
n
is. There it is. You
Yeah.
have to tell me the starting point. See, when I initially saw this, right? And this is also another reason why sequences are kind of tricky, is because like everyone has different interpretations, right? When I initially saw this, I just saw this as n squared minus 2 over 2 squared, but n would start at 2. But he's saying it's like n plus 1, but n is starting at 1. Someone else could say, I want it to start at 0, so it would have to be n plus 2 squared over n plus, you know what I mean? So all those are equivalent and correct, but all those are correct. I'm telling you, they're fine. But you know, in terms of, I think since we're gonna take the limit of this thing, I think it'd be easier if we just left it as n, because then if it's n plus 1 squared, we're gonna have to like multiply this stuff out. I don't want to do that. Yeah. So
And the final equation would be n is greater than or equal to 2, and then it's n squared minus 2 over n squared, right?
yes, so if I wanted to go in this matter, right? So this is a sub n, where it's going to be n squared minus 2 over n squared. By the way, did I lose anyone on that, right? Does that make sense? Why it's n squared and there's another n squared on the bottom, right? The minus 2's are consistent on each term, right? The only thing that's changing from term to term is the first value on the numerator and then the denominator, right? So, and because that's the case, and we want it to start at 2, n has to be greater than or equal to 2. Is that okay? Is anyone lost on that? I know, like I said, some people pick this up kind of quickly, some people not so much. But if that's you, if you're kind of having trouble, it's okay. You know, we'll do more examples and you'll get it. How do we do this? How do we figure out what this sequence is going to? There's a ton of different ways to do this. All right. We need to take the limit as n goes to infinity of our explicitly defined sequence. Now, how would you guys normally do this?
Plug in infinity for n, right?
Oh, you almost made me spit out my tea. Oh my gosh. How dare you? You cannot, guys, okay? You guys are gonna hurt me. In math, okay? Infinity is not a finite value. It is not like a variable that you can kind of just plug in. So please watch your words. It's like offensive, all right? You cannot plug in infinity. Some of you try to do this on the last test with the improper integral. You need limits, okay? You can say the words, oh, we're gonna let n go to infinity. That's fine. But if you say the words plug in infinity, like the mathematicians will laugh at you, and you don't want that, right? So please, don't say plug in infinity.
All right, my bad. I didn't mean.
I don't mean to pick on you, Jeremy. But
it's cool.
What? So
I'm used to it.
Oh, that's kind of sad. I'm sorry. What would you say instead then? Like, how would you direct me to finish off this problem then?
You're asking me in particular, or
yeah, or I mean, if you don't want to talk, if I shamed you enough, if someone else wants to talk to, it's cool to me.
Yeah, I'm shamed. I'm sorry.
Anyone else? How do we do this? Please don't use the words plug in infinity. But it's okay, Jeremy, because I know like there's at least like 3 or 4 other people in here that were like saying the same thing.
Yeah, okay, I'll use what you said and say let n go to infinity.
Okay.
And observe what happens. You see 2 is a constant, and as n approaches infinity, that 2 will become less significant. So you could be like, when n is approaching infinity, that 2 is basically gonna, like, you won't even notice it and it'll approach infinity.
Now, that is correct. And if Justin wanted to write all that down, that's cool. It's a lot of reading on my part, but why don't we learn how to do this like the algebra way, right? Does anyone know what I'm talking about here? No, we're not sure.
Limit rules that you mentioned before?
I guess you can do that on this one, sure. Break it up into 2 things and then go from there. There's something I want to show you guys though, because not a lot of my students didn't know this before my class. You can divide by the highest power. This is like a common trick. It's actually something that a lot of people kind of they're like, oh yeah, of course you can do that, but like they don't think about it at first, you know? What is he talking about? You know, if you have a fraction, right, as long as you do the same thing to the top to the bottom, right, in terms of multiplication or dividing, the fraction keeps its value. For example, if I change 2/4 to 1/2, it's the same value, right? It's just wearing different clothes, you know? So in this case, I'm gonna divide everything by the highest power. I'm allowed to do that. I'm dividing the top by n squared, dividing the bottom by n squared. Therefore, I'm technically multiplying by a factor of 1. Do you guys see that? So what am I left with? This becomes 1 minus 2 over n squared over 1. This is a stronger argument. This is a more simple argument, I would say, than what Justin was saying. Justin was absolutely right. He was saying the 2 becomes insignificant, therefore, and the power on top matches the power on the bottom, therefore the answer is 1, right? But you would have to write all those words down. And do you want to do that? No, that's a lot of writing, right? So this is much shorter. You can actually just say from here, this is going to go to 0, leaving you with 1. Do you guys see the difference? Yeah. Okay. Cool. Questions on this so far?
Would it be okay if we did it with the limit rules? Because that's how I initially approached it.
For the ones that you can, yes, absolutely. But sometimes it's easier to do it this way. That's why I'm showing you this way. Okay. There was something else I wanted to say about this and I don't remember. I'm just gonna move on. I'm running out of so much. I'm running out of time. Yeah, I might
have a
to-
question.
I might have to ask Gina to do this with you guys. What's your question?
I was gonna say, can you use like, yeah, low. Never mind. You got it.
I'm a mind reader, I know. Yes, you can use L'Hopital's rule. I'm gonna kind of like breeze through this example because you guys should know how to use L'Hopital's rule, but there is one caveat. Do you guys know what the catch is with L'Hopital's rule? Can I just do this? Can I just do that? Is that enough work? Is that proper work? Does that make sense to the reader? You can probably tell by the tone of my voice that no, obviously not. Okay.
No.
You you can't do this. What you are saying in your work is that this statement is this statement is equal to this. That is not true. You limit of n goes to infinity of n plus n over n squared is not equal to 1 plus 1 over n over 2n. You can't say that. Those are two very different expressions, right? So you need to be clear in your work in what you're trying to say. Otherwise, it gets points off. If you're trying to use L'Hopital's rule, you need to show indeterminate forms first. That is the pre thing, the oh my gosh, what's the word I'm thinking of? That is the thing you need to use L'Hopital. If it's not indeterminate, you can't use L'Hopital. That's how you guys learned it, right? In this case, this is going to be infinity over infinity. There's my indeterminate form. Therefore, I can say that this is equal to the limit as n goes to infinity of 1 plus 1 over n over 2. Okay, please, you can't cut out the middleman. You can't cut this step out. Without this step, you're doing something illegal. All right, and then you go to Math Joe. And then from here, then you can say, right, this is going to become infinity on the bottom and then 1 on top, which is 0. You guys know about that, right? Like infinity on top and constant on bottom, and then infinity on bottom, a constant on top. You know, like, do you guys, like, if I have infinity over a number, what does that equal to?
Infinity.
It's infinity, right? How many times can you divide infinity? It's infinity, right? Or
It's
like,
infinite.
if I have like 1 over 0, you guys, is this indeterminate? It's infinity.
Oh no.
It's not indeterminate. You can determine the answer. It's infinity. Okay. These are very common pitfalls. A lot of people screw up a lot. They think 1 over 0 is indeterminate because it's infinity. Nope, it's not true. 0 over, the only indeterminate forms that you guys should have learned, and there's a couple more, but the main ones are 0 over 0 and plus minus infinity over plus minus any positive negative infinity over any positive negative infinity. These are the only two indeterminate forms. Anything that doesn't look like this, you can't use L'Hopital's. Okay? Okay. Moving on. Is that it? Can I move on to, damn. We'll get to geometric series later. I'm gonna tell Gina to do the squeeze theorem with you guys. Squeeze theorem is on page, where is it? Page 50, 558. So this is a squeeze theorem. And I'm gonna tell Gina to do this with you guys. This you guys will probably do this on Thursday because tomorrow's recitation will cover the stuff from lecture 5 and the review. Okay. That leads me to section 10.2. So I'm just going to title this geometric series. So 10.2 introduces the idea of now a series, not a sequence. A series, not a sequence. A series, not a sequence. Why am I emphasizing this so much? It's because students all the time mix up sequences and series, all right? Some things are transferable, some things are not, but it's easier in your mind just to think them as two separate entities. They are related, but they are not the same, okay? Please don't make that mistake, all right? What is the clear difference between a sequence and a series? A series is a sum of a sequence. Did I get that grammar right? A series is the sum, sorry, the sum of a sequence, sorry. Meaning the terms are no longer separated by commas, they're separated by plus signs. So we need different notation. So here we go, ready? Here's the notation. It's a summation sign. It's called sigma. You can do the little doodlies here if you want. It's up to you. I just do the regular sigma thing. Index is still referred to as n. And it usually goes up to infinity or it goes up to a finite value. It's like, it depends on the problem. And we are taking the sum of a sequence. Yes, questions on the notation? Have you guys seen series before? Maybe, sort of.
A little
When
bit,
we
yeah.
were being introduced to integrals, we saw a bit of series.
Say that one more time, what?
When we were being introduced to integrals, we saw a bit of series.
Oh, wow, then you had a good teacher. That's good. Yeah, because think about it, guys, right? When we're doing integrals, when we're adding up an infinite amount of Riemann sums, right? That's where this comes from, right? Anyways, whatever. So this means this is going to be a sub 0 plus a sub 1 plus a sub 2 plus yada 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 yada. And what you can kind of glean from this is that, or what we're going to go into next is we're going to be summing up an infinite amount of terms, which is, it sounds paradoxical. It sounds kind of crazy, right? But it's not something we haven't seen before. Think about it. When have we looked at something that goes out to infinity, but it still like gave us like a converging answer?
Improper integral.
Yeah, we're gonna see improper integrals kind of make a comeback in one of the sections, all right? But yes, that's essentially the idea. We're taking something and we're taking a sequence, adding up all the terms and seeing if the thing is gonna converge or diverge, all right? We're gonna learn a bunch of these tests. We're gonna learn a bunch of different ways to show that something converges and diverges using logic, right? We love logic, right? So the first types of series I'm going to introduce to you guys is geometric series, because that's just kind of like the order the book goes in. So what is a geometric series? A geometric series is when you multiply. Yeah, I'm just going to. Geometric series is defined as this. All right. Oh, whoops. Sorry. N is equal to. Does it start on 1 or A? I think it starts on. Hold on. Where is it? Yeah, we're not gonna do telescoping series. All right, here we go. It starts at 0, goes to infinity. The book uses C, I use A. Same thing. The way it's defined, it goes, A is the first term, and R is what's called a common ratio. It's the thing that's being multiplied to every single subsequent term. So if I string this out, it starts on A. The next term is going to be A times R, right? Because you're multiplying R to every subsequent term. And then you're going to multiply R again. So it goes AR squared. And you multiply R again, AR cubed, and so on and so forth. All right. And geometric series are really cool. There's a really easy way to tell if this thing is going to converge or not. I usually show you guys. I guess I got to do the video. Man, what happened? How did I lose so much time? I'll show you in the video. It's going to be a short video, but I'll show you where the formula comes from. But it basically says there's two things you're looking for. And you need to say these two things if you're trying to show that a certain series is converging, okay? So first thing is, does the series look geometric? Right? This is something you can easily identify. Is there a common ratio being multiplied to every single term? And then does it start on a certain A value? Right? So you need to state, yes, the given series is geometric. The second thing you need to say, look at is the common ratio, because the common ratio can be positive or negative. If the common ratio is less than 1, the series converges to A over 1 minus R. They use S to denote like the sum of the series. So they're basically saying the sum of the series will equal the first term over 1 minus the common ratio. The other conclusion is if absolute value of R is greater than 1, whoops, the series actually diverges. This is essentially a geometric series in a nutshell. Any questions? We're gonna look at one or two quick examples. Hopefully I can get to it. Ready? All right. So example, I don't know what number I'm on. Let's say 4. Here's an easy one. So n is equal to 0 to infinity, 5 to negative 1. And the directions for this is probably going to be something along the lines of, does this series converge or diverge? If so, oh, I'm sorry, if convergent, find what the sum is. Right, because if it's divergent, it's just going to diverge to infinity or just not settle on a number. Now, this is an unacceptable answer. Ready? That's an unacceptable answer. I will give you negative points if you do that. If you just say converges or diverges with no explanation, with no justification, no, that's worth 0 points. I don't even care if the answer is right. Like that the numbers that you get are right. Do we understand? Is that clear? This is not an acceptable answer. Is that red or orange? Damn, I've been using orange this whole time. Or whatever. That's not an acceptable answer. You need to say the proper justifications for why you believe this thing is convergent or divergent. Your logic must flow. Yes. So how do we do that? All right. Well, let's look at this thing a little bit more closely here. That negative n, this, I can rewrite this as so times a 1. And oh my gosh, what do I see here? Well, if I plug in the first couple values, right, it goes 1 plus 1/5 plus 125 plus. So I can say this is a geometric series where a is equal to 1 and what's the other thing that it needs to have to be a geometric series?
Common ratio.
A common
Right.
ratio, and r is equal to 1/5. Do you guys see that? Do you guys see how I'm explaining in my work that this is in fact a geometric series where a is one, it has a starting value and it has a common ratio. Therefore, it has to be a geometric series. Okay, so boom, that first part's done. Check. Second part, I say it up here. One of two things can happen, right? Since in this case, the absolute value of r is less than 1 because it's 1/5, right? The sum equals 1 over 1 minus 1/5, which is 5 over 4. I know right now it doesn't make sense why. Watch the video if you are curious. If you're not curious, then whatever. But I'm going to explain in the video like why this is the way it is, all right, with a nice, well thought out and well explained example. But just for time's sake, I need to just show you guys the formula, even though I hate teaching like that. But that's it. This is a proper like smiley face, like type of answer. All right. Please do not do this. Is a poopy answer. Okay. Don't do this. This one smells. Those are stinky lines. Okay. Please don't give me an answer like that. I will give you a 0 immediately. You need to say proper justification and then your conclusion. Wait, did I say conclusion? Oh my gosh, I didn't say the conclusion. Sorry. So this is a geometric and the wait, since the series converges. Sorry, I forgot to say that. Series converges to S, which is equal to blah 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 blah. All right. I forgot to answer the question, right? The question says, does it converge or diverge? You got to make sure you answer the question. My bad. We are going to learn 6 other tests. This is like, quote unquote, one of the tests, but we're going to be learning 6 other tests with their own criteria and things like that. And you're going to need to say X, Y, and Z to get to your final answer. So please get the practice in now. I'm not testing you on your algebra, right? Like this, I don't really care about. I care about this, like how not elegant, how does your logic flow, right? Are you looking for the A? Are you looking for the R? And then what does your write-up look like? Does that make sense? That's what we're going to be looking for in the homeworks and stuff. Do we have any questions on geometric series? You're going to do some more examples with Gina in the next recitation. There was a lot of stuff I couldn't get to, so I'm going to be making a supplemental video. If you guys have questions, please let me know, but please focus on studying for your midterm this Wednesday. All right, once again, this Wednesday, I know some of you have your cameras off for whatever reason, but you've been not warned. You've been told about this midterm and the final well in advance. There should be no excuse for on Wednesday for you to say, oh, I'm like, I can't do it or whatever. You need to, if that means you need to like sit in your bathroom or whatever, I don't care. You need to find a spot where you're not going to get distracted, where you're not going to, I know some of us don't have that, but as best as you can, all right, please try to arrange it. You know what time your midterm is and everything, okay? You're gonna have 1 hour. As soon as you come in here, I'm not even gonna say go, it's gonna be open. Just go, like you make sure you're set up. You're gonna have the full hour for it. And yeah, that's pretty much how it's gonna go. But you gotta make sure that you have your camera on and all that jazz, all right? Once again, this, hold on. This is not acceptable, all right? I can't see anything. All I see is forehead. All right, please show right here, moneymaker, yes? What else? Mic needs to be on. Speaker should be low, no hoods, no headphones, all that jazz. Okay, questions? All right, guys, please reach out if you need anything. If not, I'll see you guys on Wednesday. Please study, please study, please study, please study.